Welcome to my YouTube channel. I am Vasant Naik from Government First Aid College, Kumta. This is the fourth session of the Unit 1 Frame of References prepared by our Carnatic University, Dharwad. In this video, I am going to explain you about rotating frame of reference. Let us watch one video to understand the definition of rotating frame of reference and Coriolis force. Here we have two frame of references. First one, the frame of reference which is at rest, is the wooden plank. This is the frame of reference which is rotating with uniform angular velocity. And let us watch what happens if a particular object is placed on the rotating frame of reference. That is, we have to place a particular object on the rotating frame of reference. See here, this is the frame of reference which is rotating with a uniform angular velocity omega. We have to take one object and place it on the rotating frame of the reference. See here, if you place the object on the rotating frame of reference, then some force is acting on that particular object. That is, without applying any external force, the object moves and it falls down. Because this is a one kind of the pseudo force, it's not a real force. That is, we are not applying any external force on it. So we simply place the object on the rotating frame of reference, but due to the force which is gained by that particular object due to the rotation of the frame of reference is called Coriolis force. Let us derive an expression for the acceleration of this particle with respect to this rotating frame of reference and with respect to the frame of reference which is at rest. Let us take a frame of reference S here, which is at rest. It has X, Y, and Z coordinates. I, J, K are the unit vectors corresponding to the frame of reference, which is at rest, and P is a particle The coordinates of the particle P are x, y, and z. Here r is the OP, that's the position vector of the particle P. Now that position vector r of the particle P is given by r equals to ix plus jy plus kz. Now, to consider another rotating frame of reference, already I have shown you in the video. That is, you have to take another frame of reference which is rotating with uniform angular velocity omega. Therefore, that frame of reference rotates, the x changes to x dash and the y changes to y dash, z changes to z dash. That is, at rest, the both frame of references are coincide, but when another frame of reference rotates, then it changes its position. It forms an angle theta. Now, we have to find the position vector r dash with respect to the frame of reference s dash. Here we have taken r dash is the position vector of the particle P with respect to the rotating frame of reference, which is rotating with uniform angular velocity omega, is equals to r dash, that's equals to I dash x dash plus j dash y dash plus k dash z dash. One thing you have to remember here, observer O and the O dash are at the same point. That's why the position vector r and r dash are same. For example, if there are two persons in the same position, one person is at rest and another person is rotating about his own axis, and if both the observers are observing a particular event in the space, then the distance of that event for the observer who is at rest and the observer who is rotating about its own axis is same. For position vector for O, position vector for O dash is same. That's why we can write the equation r is equals to r dash. Therefore, r is equals to I dash x dash plus j dash y dash plus k dash z dash. This is the equation number 3. Now, for the observer O dash, the frame of reference S dash is not rotating and its unit vector remains constant. If I have to differentiate in the equation 2, so this is the equation 2. This equation I have mentioned in the previous slide. So what happened here, you have to consider the observer O dash and he is in the frame S dash and that frame of reference is rotating. Then according to the observer O dash, the frame S dash is at rest. This is if you are in the moving vehicle, inside the moving vehicle, you think that we are at rest, the seat is at rest and our co-passenger is also at rest. Therefore, for observer O, the frame of reference S dash is rotating, but for the observer O dash, the frame of reference S dash is not rotating and its unit vector remains constant. Therefore, you have to take this equation and differentiate it with respect to the time. You get differentiation of r dash with respect to time, dr dash by dt is equals to I dash, because unit vector is remain constant here. That's why I dash differentiation of x dash is dx dash by dt plus j dash is constant dy dash by dt plus k dash dz by dt. And let us take here dr dash by dt is nothing but a velocity. Therefore, v dash that's equals to I dash dx dash by dt plus j dash dy dash dt plus k dash dz by dt. Let us take this as equation number 4. Now to take v dash. What is v dash here? V dash is the velocity of the particle measured by the observer O dash relative to its own frame of reference S dash. Now for the observer O, the frame of reference S dash is rotating and its unit vector also changing the direction. That is, the I dash, Z dash and K dash are also moving. Therefore, I have to differentiate the equation 3. So this is the equation number 3 which I mentioned in the previous slide. Therefore, differentiation of r with respect to time dr by dt. Here I dash is changing, x dash is changing. Therefore, I dash dx dash by dt into x dash di dash by dt. That is the differentiation of q into v. Here I dash into differentiation of x dash with respect to time plus x dash differentiation of I dash with respect to time plus z dash into differentiation of I dash with respect to time plus y dash into dj dash dt plus k dash dz by dt plus z dash dk dash by dt. So this is the equation number 5. The endpoints of unit vectors I dash, z dash and k dash are in uniform circular motion with angular velocity omega relative to observer. Now we know that the relation between the velocity, linear velocity and the angular velocity. R is the position vector. V is equals to R omega. Or we can write V is equals to dr by dt. Similarly, we can write di dash by dt is equals to, that is V equals to R omega here. Therefore, di dash by dt is equals to omega I dash. That is the R by dt is equals to R into omega. Therefore, here the position vector is R. Here you have to take the unit vector I dash. Di dash by dt is equals to omega I dash. Dz dash by dt is equals to z dash omega and dk dash by dt is equals to omega into k dash. Substitute in the equation 5. This is the equation 5. Let us substitute the equation here. That is omega into I dash. This is di dash by, here you have to take I dash dx by dt. These three terms as it is. Then right here di dash by dt. Di by dash by dt value is omega I dash. Therefore here x dash omega I dash plus y dash into dz by dt value is omega z dash plus z dash into dk dash by dt value is omega into k dash. Now from the equation 3 and 4, This is the equation number 3. I dash x dash plus z dash y dash plus kz z dash, and this is the equation number 4. V dash equals to I dash dx dash by dt plus j dash dy y dash by dt plus k dash dz by dt. This is the equation number 3 and equation number 4. Now from equation 3 and 4, see here. Here dr by dt, I have taken it as a v, and I dash dx dash by dt. This is equation number 4. This is equation number 4, and here omega is common. We can write this equation as omega into I dash x dash plus j dash y dash plus kz k dash z dash, because omega is common here. Therefore, we can write here this is omega r. Therefore, dr by dt is v. This is the equation number 3 plus omega into equation number 4. So this equation. Therefore, v is equals to v dash plus omega r. This is the equation number 6. Remember this equation, v equals to v dash plus omega r. Here, v is the velocity of the particle as observed by observer O, and v dash is the velocity of the particle p as observed by observer O dash. Now let us calculate the acceleration. The acceleration of the particle as observed by O relative to frame of reference S dash is given by acceleration is rate of change of velocity, that's equals to I dvx by dt plus j dvy by dt plus k dvz by dt. That's the equation number 7. Now the acceleration of the particle p as observed by the observer O dash relative to frame of reference S is given by here a dash equals to I dash dvx dash by dt plus j dash dvy dash by dt plus k dash dvz by dt. Now differentiating the equation 6 with respect to time, taking omega to be constant, because frame of reference S dash is moving with a uniform angular velocity. Therefore, here omega is constant and the position vector is same for both the observers. But you have to take the differentiation of equation number 6. This is the equation number 6 here. Here you have to write dv by dt plus dv dash by dt plus omega into dr by dt. I have to take omega as a constant term. Now differentiating equation 4 with respect to t. This is the equation number 4. Here I have mentioned the equation 4 here. Now let us differentiate the equation 4 here. This is dv dash by dt is equals to, again differentiation of u into v, I dash dvx by dt plus vx dash, here dx dash by dt is nothing but vx dash into di dash by dt plus z dash. Here you have to take differentiation of this velocity term dvy dash by dt plus vy dash. This is the vy dash is the velocity term, vy dash into differentiation of dz dash dt plus k dash into differentiation of this velocity term vz. This is the vz term for differentiation of Vz dash by dt plus is the Vz dash, sorry, Vz dash into dk dash by dt. Now after simplification, we get to take the last three terms here. In the last three terms, we know that di dash by dt is equals to, this v equals to r omega. That's why I have to write here I dash into omega, and here dz dash by dt becomes z dash into z dash cross omega. Here dk dash by dt is equals to k dash cross omega. Therefore, that equation here, this is the equation for a dash, and the remaining equation, the omega is constant, is omega into I dash vx dash plus j dash vy dash plus k dash vz dash. So you get a dash plus omega into, so this is the equation of v dash. For dv dash by dt is equals to a dash plus omega cross v dash. Now from equation 6, this is the equation number 6 here. Now from the equation 6, this dr by dt. Now from equation 6, this is the equation number 6, v equals to v dash plus omega cross r. Here v is nothing but dr by dt, that's equals to v dash plus omega cross r. Here I have to take this as equation number A and this as equation number B. Now substituting the values of A and B in equation 9. This is the equation A and this is the equation B. And this is the equation number 9. These equations are mentioned in the previous slides. Substitute the value of equation A and equation B in equation 9. For here dv by dt, that's equals to dv dash by dt. I have to substitute the equation A plus omega into dr by dt. That is dr by dt value is v dash plus omega r. If I have to write here, this is the equation number 9. For dv by dt is equals to, we substitute the value of equation A plus omega cross, substitute the value of equation B. There you get dv by dt is equals to equation A plus omega into equation B. Here dv by dt is nothing but acceleration. Therefore, acceleration is equals to A dash omega cross v dash plus omega cross, to multiply here omega cross v dash plus omega cross r. Now after simplification, I get the equation number 11. That equation 11 is A equals to A dash. These are the two terms, omega cross v dash. If I had to write 2 times omega cross v dash plus omega cross r. Here A is the acceleration of particle P as observed by the observer. A dash is the acceleration of the particle as observed by the observer. O dash. Now this term is important. 2 omega cross v dash to the Coriolis acceleration. That is omega cross r is called centripetal acceleration. Now the equation 11 can be written as, write this equation 11, a dash is equals to a minus 2 omega cross b dash minus omega cross r. Here minus omega cross r is the centrifugal acceleration. Here the positive term centripetal acceleration, the negative term centrifugal acceleration. Now the total force acting on a particle of mass m as observed in rotating frame of reference S dash is given by, this is the equation number 11. Now right here F dash equals to, for a particular mass ma dash here, for this is F dash, ma dash is nothing but F dash. If F dash is equals to ma dash is equals to, I have to multiply with the term m, then you get F dash equals to m into a minus 2m omega cross v dash minus m omega square r. Therefore we get F dash is equals to, this is F minus 2m omega cross v dash minus m omega square r. When the particle is at rest with respect to rotating frame of reference, if I were to take v dash is equals to 0 here, this term v dash equals to 0, then f dash is equals to f minus m omega cross r. Here the centrifugal force minus m omega cross m omega cross r is a fictitious force acting on a particle at rest in a rotating frame of reference. Here the Coriolis force is a fictitious force and its value is minus 2m omega cross v dash. Its value depends upon the relative velocity of the particle with respect to the rotating frame and also the angular velocity of the rotating frame of reference. Here what is Coriolis force? Coriolis force is a fictitious force appearing to be acting on a particle due to rotation of frame of reference. In the video you have watched, when you placed a particular object on the rotating frame of reference, even though without applying any external force on the particle, due to the rotation of the frame of reference with angular velocity omega, that particle falls down without applying any external force. Therefore, that force is called Coriolis force, which is acting on the particle due to rotation of the frame of reference. Thanks for watching.